So this video is on free energy change and entropy change. And our aims for this video are to understand the idea of entropy and how this relates to the feasibility of reactions, calculate entropy changes from absolute entropy values, and know the relationship between free energy change, entropy change, and entropy change, and use this relationship to calculate the temperature at which reactions become feasible. So entropy is simply the measurement of disorder, and that means that if we, for example, were to boil water, then we would be increasing entropy because we are increasing disorder or randomness. Similarly, if we were to, for example, do a reaction where we are creating more species than we started with, then that is also increasing entropy, it's increasing disorder. And this is favourable. And the reason why it's favourable is because if we increase entropy, then that makes reactions more feasible. If reactions have an increase in entropy, that usually makes them more feasible. And the reason for that is that for a reaction to be feasible, delta G, or the free energy change, needs to be equal to or less than 0. And the relation between delta G and entropy is that delta G equals H minus T delta S, where delta S is our entropy change. Now, if our entropy change is positive, i.e. things become more disordered, then this value here will always be negative. And so that makes the likelihood of delta G being negative as well more likely if this is negative. So in order to calculate the entropy changes from absolute entropy values, all we need to remember is that the change of entropy will equal the sum of the entropies of the products minus the sum of the entropies of the reactants. So if we take this example here, it says an equation for reaction in the hard process shown below together with some entropy data. And there's the equation. We've got to calculate a value of the entropy change for the formation of 1 mole of ammonia. So we've got the entropy values here for the 3 different species, and so we've just got to use the equation. So delta S equals the sum of the entropy values of the products, or the product in this case, minus the sum of the entropy value of the reactants. So that's going to equal 193 for the ammonia. Take away 192 divided by 2 for the half N2, take away 3 over 2 times 131, and that equals minus 99.5 joules per Kelvin per mole. Now it's important you realise that these entropy changes are usually in joules per Kelvin per mole because the enthalpy changes are always in kilojoules per mole, and it's important that you convert one or the other into the same value for energy. So in order to calculate temperature at which reactions become feasible, we need to know the relationship between free energy change, enthalpy change, and entropy change, and we've mentioned that before. So delta G, our free energy change, equals the enthalpy change minus temperature times the entropy change. Now, for a reaction to be feasible, delta G needs to be negative, and so when the temperature at which the reaction becomes feasible is when delta G equals 0, which means if we rearrange this, we get 0 equals delta H minus T delta S, and so therefore we get T delta S equaling delta H, so you can then rearrange this to get T equals delta H over delta S, and that's what we can use in order to work out the temperature at which reactions can become feasible. So we can use the data here in order to work out when this reaction becomes feasible. So it says use data from the table on page 4, that's the data here, to calculate the minimum temperature above which this reaction is feasible. So the first thing to do is to work out the entropy change. The delta S equals delta S of products take away delta S of reactants. So NO is 211.1. And we're going to take away half of N2, so 0.5 times 192.2, take away 0.5 times 205.3, and that equals 12.35, and that's in joules per Kelvin per mole. Now, what we want to do is convert that into kilojoules per Kelvin per mole, so we need to divide that by 1,000, and that equals 0.01235 kilojoules per Kelvin per mole. The reason we want to do that will become apparent in a bit. Now, for this reaction to become feasible, delta G must equal 0, and therefore T will equal delta H over delta S, which I showed you in the previous slide. So delta H is going to be just simply 90.4, because that is the formation of the P4NO, which is what this reaction shows. So we've got 90.4 divided by, which is in kilojoules per mole, which is why we had to convert our entropy change into kilojoules per Kelvin per mole. We're going to divide that by 0.01235, and that will give us our temperature of 7,320, and this is in Kelvin.